Welcome to the Audio Precision Audio Connections online tutorial. In this lesson, you'll learn the basics of audio connection circuits, connectors and grounding for audio test and measurement using audio precision instruments. We'll cover the two analog connection circuit types, mini audio connectors and grounding, as well as identifying and correcting poor connection conditions, which are the most common source of audio testing problems. We'll also take a look at digital audio circuits and connections. I'll assume you're familiar with the tools and menus in Audio Precision control software, as well as the interface for Audio Precision online training. If not, please view the AP2700 Quick Start tutorial, which you'll find on the Learning Center online training homepage. You can click the Audio Precision logo at the bottom right corner to jump to the Learning Center. Otherwise, click the Continue button when you're ready to proceed. There are two analog connection circuit types, balanced and unbalanced. Balanced audio circuits usually consist of three conductors: the cable shield and ground, the positive going phase or high, and the negative going phase or low. A balanced audio signal is differential and therefore has immunity from noise that could otherwise couple into the cable from an unwanted source. The two signal lines, a twisted pair, have equal source impedance. That's the important part. And they reference each other, not ground. High and low, or positive and negative, are inverted 180 degrees out of phase from each other. When an external electric field intersects a balanced cable, it induces noise on both the positive and negative going lines equally. At the receiving end, the differential input circuit subtracts the negative signal line from the positive signal line, and the noise is canceled or rejected. This is also known as common mode rejection. The measurement of this is common mode rejection ratio, or CMRR. Balanced audio lines can be run over long distances with virtually no noise induction and are suitable for professional applications. Traditional telephone lines are of this type. Balanced audio circuits can be grounded or floating. A typical balanced output usually has an active balanced output circuit. However, most audio precision instruments use a transformer with the center tap grounded. A characteristic of balanced to ground outputs is that half the output voltage appears between each line and ground, -6 dB on each, positive and negative. The signal is differential. However, the cable shield can be part of a ground loop. When using balanced ground in audio precision instruments, connect to the XLR connectors in the analog I/O. Select the balanced ground configuration in the analog generator panel and XLR balanced in the analog analyzer panel. Balanced floating output circuits have no ground reference at all. The output is transformer coupled. Ground loops in the signal are not possible. However, the cable shield can be part of a ground loop. When using balanced float in audio precision instruments, connect the XLR or double banana connectors in the analog I/O. Select the balanced float configuration in the analog generator panel and XLR balanced in the analog analyzer panel. Audio Precision ATS-2 instruments are different. They use an active balanced output circuit. A ground loop is always a possibility with these instruments. The most common balanced audio connector is the XLR. In the XLR connector, pin 1 is the cable shield, pin 2 is the positive going phase, and pin 3 is the negative going phase. Another connector commonly used is the quarter-inch phone, tip ring sleeve or TRS, where the tip is the positive going phase, the ring is the negative going phase, and the sleeve is the cable shield. The less common miniature XLR and LEMO connectors are generally used on small audio devices. The double banana connector is used in balanced floating circuits. There's usually a low side or negative pin indicator tab. Unbalanced audio circuits consist of a single signal line referenced to a ground line or chassis connection. The signal line has specified source impedance, and the ground is assumed to have zero source impedance. That's what makes it unbalanced. Unbalanced circuits have no magnetically coupled noise immunity, and ground loops are likely. The lower cost and complexity of unbalanced audio circuits suit them for consumer applications where short cable runs are normal. Unbalanced grounded circuits are typical of all consumer devices. The signal is carried on one line and referenced to ground or a chassis connection. When using unbalanced ground in audio precision instruments, connect to the BNC connectors in the analog I/O. Select the unbalanced ground configuration in the analog generator panel and BNC unbalanced in the analog analyzer panel. Unbalanced floating circuits are not common since a transformer is normally required. The ground loop possibility is removed, but the signal is not immune from noise. When using unbalanced float in audio precision instruments, connect to the BNC connectors in the analog I/O. Select the unbalanced float configuration in the analog generator panel and BNC unbalanced in the analog analyzer panel. This is a recommended connection because it removes the possibility of a ground loop. The RCA phonoconnector is the most common unbalanced connector in use, and unfortunately, it's also the most unreliable. The BNC connector is more durable, and it locks into place. Quarter-inch phone connectors are common in pro audio equipment and can be tip sleeve for mono or tip ring sleeve for stereo applications, where the tip carries the left channel, the ring carries the right channel, and the sleeve is the ground reference. Many small consumer devices and personal computers use the 2.5 mm or 3.5 mm equivalents of the quarter-inch phone connector. The balanced-to-balanced connection is the best analog audio interface. It has the best noise immunity. Variation in source impedance, cable capacitance, and twisting uniformity affect just how balanced it is. The accuracy of source impedance is important. It directly affects the common mode rejection ratio. Balanced to unbalanced connections are okay if they're floating. There isn't a ground reference. Grounded balanced-to-ground connections require different wiring. Otherwise, one of the outputs is short-circuited. The unbalanced-to-balanced connections are not a problem. The differential input doesn't care whether the reference is ground or a signal. The noise immunity isn't there since the source impedance isn't equal on the two lines. Unbalanced to unbalanced connections are the worst possible. There's no rejection of ground noise. Different impedances of the two lines ensure sensitivity to magnetic fields. Cables are often made with poor or no shielding, so RFI can be a problem, and since input circuits may have nonlinearity, RF signal detection can occur. Any difference in potential between the grounds at either end of the cable will show up as noise. This ground difference potential is often AC mains, so the noise will show up as hum or buzz. Connection problem sources include poor connector contact resulting in high contact resistance, AC mains related hum from ground loops, AC mains hum picked up inductively by the cable, RFI, radio frequency interference, AC buzz from television vertical interval, high tone from television horizontal, and lamp dimmer, triac, and motor brushes can pollute the AC mains ground. Hum and noise are caused mainly by three sources. Number 1, electric fields such as fluorescent lights, CRT computer monitors, or any high-voltage source are examples. Shielding is very effective in reducing or eliminating the problems. Number 2, magnetic fields. All electric currents create magnetic fields and vice versa. Avoid running signal and AC lines parallel to one another. If signal and AC lines must cross each other, cross them at 90 degrees. Twisted pair signal conductors can help in balanced circuits. Star quad cable works well, but with much higher cable capacitance. Number 3, polluted ground is a ground with AC mains leaking in or simply a poor physical connection to earth. Replacing the third conductor ground in typical AC connections with a large direct heavy gauge ground will help. Ground loops can occur when more than one path to ground exists. Because there is always some finite resistance, the difference in potential causes equalization currents to flow through signal lines. Ground loops are almost unavoidable in unbalanced lines. This illustration of a typical consumer AV system shows how problems can occur. All lines are unbalanced, and there may be multiple connection points to AC mains causing ground loops. Induced hum from AC wiring running parallel to signal lines, RF, electric motors, video monitors, and light dimmers compound the problem. Professional audio facilities use a star ground system, which is a single central earth ground point. Each chassis has a separate large conductor connection to the star, which is not related or connected to the AC mains grounding. Facilities with multiple stations or rooms build a star of stars. Brute force grounding will reduce ground loop-induced hum by supplying a much lower impedance connection for potential difference equalizing current to follow. A large multi-strand or braided cable is used, number 10 or 12 for short runs, and up to double-aught gauges for longer runs. You can check test results with and without a brute force ground strap to determine when it's needed. When using a brute force ground strap with audio precision instruments, connect one side of the ground to the ground lug on the analog output or input. Connect the other end to the chassis ground on the device under test. Telescoping grounds are balanced lines with shields connected at one end only. Be consistent in which end you connect, and the signal path will be ground loop free. This is a common practice in recording studios and broadcast facilities. We have several methods of testing for connection problems. The brute force method uses an additional, separate, lower resistance connection. We can filter out the low frequencies by applying a high-pass filter and check for significant improvement. Spectrum analysis provides a detailed look at problems, but requires a high dynamic range FFT analyzer. To use the brute force method, conduct the test with and without the ground strap, then compare the results. In this low noise example, we see a peak of -122 dBV at the mains frequency without the ground strap, and -138 dBV with the brute force ground. That's a 16 dB improvement. We can also see some improvement at the second and third harmonics. Ground loops can also be created by adding a brute force ground strap, so caution must be taken. To use the filter method, make a noise or THD plus N test with absolute units, volts, dBu, or dBV, and switch in a 400 Hz high-pass filter. An improvement of more than about 0.4 dB is an indication of some low-frequency components. These are normally AC mains-related frequencies. FFT spectrum analysis produces a very detailed look at possible problems. It will always show some AC mains frequency. Higher AC in one channel means internal electronics are closer to the AC on that channel. Second harmonic can indicate full wave or bridge rectifier filter inadequacy. Third harmonic is common in buildings with three-phase power. Higher harmonics exist since the AC power has distortion. Higher frequency noise and spurious spikes can be created by motors, lamp dimmers, and other sources. These jump around. One common problem is that a cable shield is just an antenna, particularly in VHF. With only one end grounded, there can be a significant RF potential at the ungrounded connection end. You can get around this by using a short lead capacitance from the shield to chassis ground. In VHF RFI, 0.001 microfarad high-quality capacitors are used. However, an unfortunate choice can resonate and make things worse. Simulating a balanced connection on an unbalanced cable by placing resistance equal to the output impedance at the source between the ground connection of the chassis and the shield connection of the cable will add common mode rejection to a differential input. This means that the impedance is balanced, so induced noise is equal and can be canceled by a differential input. This works even though only the signal voltage isn't balanced. Here's a trick for connecting professional active balanced to consumer unbalanced circuits. If we use only one of the typical +4 dBu balanced lines, it is half the output voltage to ground. If we just resistively divide the voltage by 2, we're within 0.26 dB of -10 dBV, which is close enough for most work. There are two digital audio connection standards in common use today. AES-3, formerly called AES-EBU, which was developed by the Audio Engineering Society in conjunction with the European Broadcast Union, and SPDIF or SPDIF, which was developed by Sony and Philips. The former is found mostly in professional applications, where the latter is generally used in consumer applications, though a fair amount of application crossover is typical. AES-3 serial digital data is carried over a standard XLR cable, where pins 2 and 3 are the balanced data signal and pin 1 is the shield. The signal can be transported through a cable up to 100 meters in length. When using AES-3 in audio precision instruments, connect to the XLR connectors in the digital I/O. Select XLR output format and XLR balanced input format in the digital I/O panel. This interface is very impedance sensitive. Cable with accurate 110 ohm characteristic is required. Nominal voltage is 5 volts peak to peak. An alternative connection standard is AES-3ID, which uses 75 ohm coaxial cable and BNC connectors. This is an unbalanced interface that permits the signal to be transported through up to 1,000 meters of cable. When using AES-3ID in audio precision instruments, connect to the BNC connectors in the digital I/O. Select the BNC output format and BNC unbalanced input format in the digital I/O panel. Voltage should be within 10% of 1 volt peak to peak. SPDIF serial data can be carried over a standard 75 ohm coaxial cable with RCA phonoconnectors. This configuration is similar to AES-3ID. When using SPDIF in audio precision instruments, connect to the BNC connectors in the digital I/O using RCA to BNC adapters if necessary. Select the BNC output format and the BNC unbalanced input format in the digital I/O panel. Voltage should be 0.5 volts peak to peak. The optical connection is via Toslink optical fiber, a standard introduced by Toshiba. When using Toslink in audio precision instruments, connect to the optical connectors in the digital I/O. Select the optical output and input format in the digital I/O panel. If you're interested in additional training resources, or if you'd like to view this tutorial again in the future, please visit audioprecision.com and click the Learning Center link. Or select Audio Precision Web Learning Center from the Help menu in AP2700 Control Software.